So look at some key questions. Uh, yes, we have about two questions here. We look at how to go about them. Then we be asked a few very brief. So what we are going to do is very, very brief. And I think we will start with. Alright, so let's begin. So we have this question. We said the figure of this time distance was precisely refraction and amplified. We are supposed to use the graph to answer the flow. We are supposed to determine the number of interface or layers we can descend from the plots. We are supposed to determine the crossover distances. We're supposed to calculate the layer velocities in meters second. Then we are supposed to determine the thickness of the first layer. Now here I'll add using the crossover and the intercept time. So we are going to find the two and see if they will match. Now, under normal circumstance, we are supposed to draw this line of best fit. I've already drawn them. They get it. So in a question, you have the graph with the various points plotted. So you just locate your line of best fit and just draw it through, right? Now in the plot, you would have the equation of each of the lines. So this equation is for this line and this equation is for this line. Now the first line that passes through the origin is the time for the direct wave, as we all know, and the one that has an intercept is that one for the refracted wave. Now if you look at the graph, since we have only two lines, we can see from the graph that there are only two layers, with what? One interface. Right. Now let's simply say we have two layers. So from this, we have two layers. Two layers. Now, from the graph, you are supposed to determine the intercept time. Now, the intercept time is the time the direct wave becomes equal to what? The refracted what? Wave. The time for the refracted wave to get to the geophone, right? So, the time where T1 and T2 becomes equal, that is where we will have our crossover time. So, from the graph where line 1 meets line 1 meets line 2. That is where our crossover distance will be. So we just look for, so this is where they meet, then we trace it down. So let me erase this. So this is where they meet. Let me try to zoom it. So let's see. So they meet here. This is where the two lines meet. Then we trace it down. And that will give us our crossover distance. So from here to here is 20. So this is 12. This is 14. This is what 16. This is 18 and this is 20. Right, so it's very close to the 20. So I will say that our crossover distance, we say that our crossover distance, so our crossover distance will be around 19.7 meters because very close to the 20, right? and so you indicate it. So let me arrange the solution well so that you have a good representation of our work. So I, you said there are two layers, and they are saying that the crossover distance is what? 19.7 watts meters. So we are done with that part. Now the third part is to find the layer velocity, right? So the layer velocity, that's what we are supposed to find. So I'm going to do the calculation here. So we know from the equation that T1 for the direct wave is given by x over what? V1, right? And that when we compare it to the equation of the line y is equal to mx plus c, we have our gradient to be equal to 1 over what? V1, right? And so if we want V1, it's simply 1 over what? Our gradient for the first line. So let me call it M1. Now if you look at this first line, this is our first line. The line in gray color. We have the equation giving us y is equal to 1.8947 what x, right? It means that if we compare this equation, let me change the color so that we can clearly see. If you compare this equation with the equation of the line y is equal to mx plus c, it means that c is 0 and what? M is what? 1.9, sorry, 894 what? 7, right? That is M1 for the first line. That is the direct wave. So knowing that, what is the unit? We have time over what? Distance. And the unit for the time is millisecond and the distance is what? Meters. So the gradient is in millisecond per meter, right? So if we want to find the velocity of the direct wave in the first layer, is simply 1 over what? The gradient m1. So we are going to get what? V1 to be equal to 1 over 1.8947 by 10 to the power negative 3. The reason why we are bringing 10 to the power negative 3 is what? The milli. Remember, the question is asking us to find our answer in meters per second. So we have to change the milli, right? So we have this second per watt meter. Now the meter will go up. So we are going to get V1 to be equal to 1 meter over what? 1.8947 by 10 to the power of negative 3 second. Yes, plus second. Now if I continue at this side, V1 is going to be 1.0 by 10 to the power 3, because when this comes out, it becomes positive, all over 1.8947, and that is going to give us our V1. So let's see. So we have 1.0 by 10 to the power positive 3 over 1.8947, and that will give us a. So the velocity is 527.788 meters per second. So that is the velocity for the of the wave in the first layer. That is what? 527.788 meters per what? Second. Are you okay? Now we need, because we said that there are two layers, we need to find the velocity of the second layer also. Now the velocity of the second layer is as a result of what? The refracted what? Wave. And so the graph of the refracted wave is the one in orange, right? So let me erase this and let's see how we go about that one. Yeah. So let me pick the B so we work with it. So yeah, All right. So we are going to look for the velocity of the wave in the second layer, right? That is V2, and it's as a result of what the refracted wave. And from the graph, the refracted wave is the line in orange, because we know that T2 is going to be x over what? X over V2 plus what? 2/8 cos IC over what? V what? 1, right? And so the one that is going to have an intercept, that is going to be the one as a result of what? The refracted wave. And because this is having an intercept and it's not passing through the origin, that is why we are saying that this is value as a result of what? The refracted wave. Now with that being said, now with that being said, we can take the equation of that line. The equation of that line is equal to 1 point what? 1113 what? X plus 15 point what? 316, right? Now let's compare this with what? With this equation. So we are comparing this with this equation. So from this we can see that our gradient for the second line is what? Is 1.1113, right? And we know that that gradient is equal to 1 over what? V2. And this gradient is in millisecond per meter. So knowing this, then it also means that this whole thing, the intercept, that is 15.316, is equal to a 2h cos what? IC over what? V1. Remember that we change cos IC, right? We change cos IC. And so when we get there, we look at that. So the y-intercept is equal to this, and the gradient is equal to this. And so knowing the gradient, we can find what? V2, right? And so if M2 is equal to 1 over V2, then V2 will be equal to what? 1 over what? M or 2, right? And so I can see that V2 is equal to 1 over M is for 1.1113 millisecond per meter. So the meter will go up, so I can say V2 is equal to 1 meter over what? 1.1113 by 10 to the power negative 3 second, right? Now let me calm down a little bit. So I can say that my V2 is now what? 1 1.0 by 10 to the power 3, because this will come up. This will come up. No, this is just algebra. All over 1.1113. This is in meters, this is in what? Second. And so I can say my V2 be equal to, so here I'll use my calculator. So 1.0 by 10 to the power negative positive 3, sorry, over 1.1113. And that is 8. So I'll get my V2 to be what? 899.8, oh, sorry, point 847 meters per second. So I've gotten my V2. So my V2 is also 899.847 meters per second. That is the velocity for the second layer. So we are done with this. Then we are supposed to find, how do we call it? The thickness of the first layer using both the crossover distance and the time what? Intercept. The crossover distance and the time intercept. So that's what we are going to look at briefly. So let's see. Okay, let's see that question. So remember that from the refracted wave equation, we had y is equal to 1.1113x plus 15.316, right? And so the intercept time, to compare this to y is equal to mx plus c, the intercept is what? The c is what? 15.316. Now comparing this also to this equation, y is equal to x over v1, sorry, v2, x over v2 plus 2h cos ic over v1, right? If you compare it, I can see that this is our y-intercept. So I can see that 15.316 is equal to 2h cos what? ic over what? v1, right? Okay. So we want this h using the intercept. Now there is a simple formula that we have because when we evaluate this, we are going to have a very simple formula. So h is equal to ti v1 v2 over 2 multiplying square root of v2 squared minus of v1 squared. So this is the equation that we are going to use to find it. And the ti is our intercept. So here you are not going to check on the graph and read it. It's given by the what? The equation of the line. You get it? So you just take it. And remember that C is in the 15.316 is in milliwatt seconds. So don't forget. So knowing all parameters, knowing our V1, V2, our T intercepts, we can find our H. So H will be equal to H will be equal to 15.316 milli by 10 to the power negative 3, right? By V1, which is what? 527 point what? 788 by, let me count this as that and use it as by 899 point what? Point 847 all over 2 multiplying square root of 2 square root of 899.44, sorry, 899.847 squared minus what? 527.788 also was squared. So you just put it in your calculator and we see what we get. So let's see. Let me put my calculator. Let's see. So we have 15.316 by 10 to the power negative 3 multiplying 527.788 multiplying 899.847 all over 2 multiplying 899.847 squared minus 899 minus 527.788 that one two squared, and that will give us our height of what? 4.9903 meters. So that is the thickness of what? Of the first layer using what? The time intercept. So let me write it here. So let me write it here. So our Ivan using the time intercept we have it to be 4.9903 meters. Now let's see using the what the crossover. Let's see using the crossover what how do you call it? Crossover distance. What we are going to do. So using the crossover distance, we had the crossover distance to be our XC to be 19 point what 7 what meters, right? And so using the crossover distance to that is as I indicated earlier, the crossover distance is at a point where the direct wave, the time that the direct wave and the time that the refracted wave got to the geophone were the same. So the direct wave and the refracted wave, they all go to the geophone at the same time, and that is where the crossover distance is. You get it? So initially from the graph, the direct wave got to the geophone earlier, then it got to the crossover time. They all got there at the same time. Then after the crossover time, the refracted wave go to the geophone um faster than what the direct what wave. So this is the condition for the crossover what time, crossover distance. So with the crossover distance, we can find our thickness and it's given by the formula xc multiplying v2 minus v1 all over 2 multiplying square root of what v2 squared minus or v1 squared, and that will give us our thickness. So we can put our parameters in 19.7. V2 is what? 8 899.847 minus what? 527.788 all over 2 multiplying square root of what? 899 point what? 847 squared minus what? 527.788 squared, and that will give us our what? Our thickness. So let's find that using our calculator. So 19.7 multiplying the expression 899 899.847 minus 527.788. And for that one, we have 5 point what? 0, 5.02, 5.02 what? 8 meters. So using the crossover distance, we are getting our thickness to be 5.028 meters, which is close to this. So if the question doesn't specify, you take the one that you want to find your thickness of the first layer. Now, if the question specify using the crossover distance or using the intercept time, you know what to do. Now, let's see the second question. So we are done with the first side. Let's see the second question, what it is. So this is the second question that we have. Let me calm down and clear the first side. So they said, so from the first principle that for a single reflector, the total travel time t for a reflected wave through a medium of a velocity v and thickness h to a detector at horizontal offset distance x is given by the relation. So here we are going to focus on reflection seismology. Do you get it? So how do we go about it? First of all, let's you draw. Do you get it? So we have the first principle. So we have our ground surface, our focus is here, and here is our geophone. Then this is the boundary between the first layer. So this is my first layer and my what, second layer. And there is what? Reflection. So reflection, let me put, let's say this will be where the middle, so comes here like this, then goes up like that, right? So this is my focus, this is my detector. The distance, said the horizontal offset distance is what? X. So here's it, X. Then the thickness of the layer, said it is what? H, right? Now, if I draw my normal, this angle of incidence, this angle of what? Reflection. Now, in simple terms, they are asking us to find the time relation, right? So let me label FD, let me call here A. Now we're going to look at the time relation. Let's time relation. Now we know that the time for the reflected wave to travel will be equal to the distance it travels, the sum of the distance it travels over the velocity it travels with, right? So the distance it travels, first it travels from the focus to this point, that will be FA, and it will travel with the velocity of the first what? Medium, or the first layer. Then from there, from A, it will travel from A to where? D. So it will travel from A to D and also travel with the speed of the first what? Layer. That will be what? B1. With that being said, we can see from the laws of reflection that I is equal to R. If I is equal to R, then it means that the distance traveled from F to A is the same distance traveled from A towards D. So we put it here. I can say T now is equal to FA over what? V1 plus, I can say AD is the same as what? FA, now say V1. Now here, the question specify that our V1 is what? V. So we have to obey the instructions of the question. Our V1 is V, right? Here's it. Our V1 is V. So we have to follow. But this will now transform into FA plus FA over what? We will say that our V1 is V. So V. And this is going to give us a 2FA over what? V, right? And so the time will be equal to 2FA over what? V. Now, we need an expression for FA because we don't know FA. So we need an expression for FA in terms of X and what? H. Now, if you look at this carefully, if this is our normal, you know, from the laws of light, you know, when the normal makes an angle of 90 to the boundary, right? And so if you look at it, this is a right angle triangle. Look at it very carefully. This is F, this is A. Let me call this G. And so the distance from G to A is our thickness H, and F to G. Now see, because because angle of incidence is equal to angle of reflection, it means that the normal would divide FD into two equal parts. So here is going to be x over 2, here is going to be what? X over 2. So I'll say that FD is x over 2. Now we are looking for FA. If you look at it very carefully, it's a right angle triangle, and FA is what? Our hypotenuse, right? So FA squared is equal to x on 2 what? Squared, that is the base plus the height, that will be what? H was squared. Now in simplifying this, I will say that FA squared is equal to x squared over what? 4 plus what? H squared. Now in moving forward, we can see that FA squared is equal to x squared plus what? 4h squared over what? 4. I did LCM here and I simplified this, the normal fraction. You get it? Now let's move down. Now in doing so, I can see that FA now is equal to square root of what? X squared plus what? 4A squared over what? 4. And I can equally see that FA now is equal to square root of what? X squared plus 4A squared all over what? 2. So I cross multiply here, then I'll see that 2FA is now equal to square root of what? X squared plus what? 4H was squared. So with this equation that I have, let me call this equation star, and let me call this equation 1. I, I have an expression that is common to equation star and equation 1. So I can say put equation 1 into star because it's a star board. So putting it inside here, let me change it because we are getting close to our answer. We will say that T is equal to 2FA is now a square root of what? X squared plus 4A squared all over what? V. Right? Now, let me look for nice place and continue it in the camera. Let me come to this side. So in continuing, I will say that with this equation, that is T, which is equal to square root of X squared plus 4A squared over V1. I was over V, sorry. I'll say that over V, I'll say that square both sides. So T squared will be equal to open bracket square root of X squared plus 4A squared over V all squared. So I can see T squared is equal to now what? This squared will cancel this squared and here will be squared. So I'm going to get N squared. So I'm going to get X squared plus 4A squared over V squared, right? So with this, I can continue and say T squared is equal to what? X squared over V2, V squared plus 4A squared over what? V squared. So T squared, now factorizing a common thing here is squared. So I can say X over V all squared. And here the common thing here is what? Squared. So I can say 2H over what? V all squared. And I have what? 2H. So we are done with the first part. So that is the first part of the question, right? So now we've gotten the relation. Just ask the question demand. Now the second question says that, and hence derive the equation for the time travel t of the vertically reflected wave from the focus. So here they are giving us a condition. They are saying that if the wave came like this, vertically reflected from the focus. So let me use a different color so you can appreciate what we are looking at here. Oh, these are it. Now they are saying that if the reflection was like this, it will hit here and it will move back. If the reflection is like this, what will be the time? Now we can use the relation that we've gotten. When the reflection hits like this, it means that x is equal to 0. Do you get it? The wave haven't traveled through this distance x. So if the wave is reflected directly at the focus vertically, it means that x is what? Equal to 0. So from our equation that we had, our equation, let me do it here. So from our equation that we had, which was t squared equal to x squared over, x over v all squared plus 2h over v all squared. Now for this to happen, it means that x will be 0. So it means that t squared will be equal to what? 0 over v squared plus what? 2h over what? V squared, right? And so I'm going to get t squared, this will go to 0. This will go to 0. And so I'm going to get t squared over 2h over what? V all squared. And so I'm going to get what? T is equal to what? 2h over v, because I find square root of both sides and I'm going to get this. So this is the relation when, or yes, this is the equation for the time travel t of the vertically reflected wave from the what? Focus, right? So yeah, basically we are done with these questions, but I want to add maybe some theoretical question. Remember, um, for instance, if we want to distinguish when we are in the field, we want to distinguish between the reflected wave and the refracted wave, what are we going to do? So we know that the geophones that is used, um, its sensors has been placed to a certain range, So between the range of 0 to 100 hertz, we are able to detect the refracted what wave, right? Then the sorry, from 5. So so this is the question. How do we dissociate between the reflected wave and refracted wave in the field? Because when we are sending the waves, you cannot say that hey, waves for only reflection or refraction. No, you always there's going to be some form of reflection and some form of refraction. So how does the geophone work in order to detect reflected wave or refracted wave? So we know that the geophone is designed in such a way that for refracted wave, it can sense frequency between 5 to what 100 hertz. Then for reflected wave, it can sense from what 10 to what to 150. So if you want to undertake reflection seismology, you make sure the wave that you are going to generate exceed what 100 hertz. So when it exceeds 100 hertz and there is refraction, the geophone is not going to record it, but it's going to record that of what the reflection. So yeah, basically these are then one particular question. I forgot. So yeah, I think we'll end it here. If you have any question, can let us know later on. See you guys next time. Bye.